All right, for homework number 5, we're starting on page 78 with number 14, and we're supposed to find the right-sided limit as x approaches 10 of this expression. Now remember, this expression is one that we should be able to graph very quickly. It is an expression, absolute value of an expression divided by itself. So this will divide out to 1 as you go to the right of 10 and -1 as you go to the left. So because this is asking for approaching x from the right, you are approaching an intended height of 1. For this next piece, find the limit as x approaches 2, where f of x equals this piecewise function. So I'm doing this one formally, but the limit as x approaches 2 on the left is using x squared minus 4x plus 6. If I use direct substitution into here, I get 4 minus 8 plus 6. So -4 plus 6 is 2. And if I find the right-sided limit for x values greater than or equal to 2, I'm plugging into -x squared plus 4x minus 2. And that's equal to -4 plus 8 minus 2. 4 minus 2 is 2. So because the left and the right limits match up or agree, that means that the limit as x approaches 2 from both sides of f of x is also equal to 2. So that's our official limit. We want to find the constant a such that the function is continuous. So remember, for continuous, that means that, by definition, that means that because the split's at 0, g of 0 has to equal the limit as x approaches 0 of g of x. So I always start by writing out that definition. G of 0 would have me plug 0 into the bottom piece, so that's a minus 0, so that's just a. And then the limit would come from the other piece. So this is 4 times the limit as x approaches 0 of sine x over x. So I took the 4 as the constant out in front. And remember, this limit we know is equal to 1. So a is equal to 4 times 1. Therefore, a is equal to 4. Sketch the graph of any function such that the limit as x approaches 3 from the right is 1, and the limit as x approaches -3 from the left, is equal to 0. Is this function continuous? So without sketching the graph, I should be able to say no, because the limit as x approaches 3 on the right of f of x is not equal to the limit as x approaches 3 on the left of f of x. Or you could also just say no, because the limit as x approaches 3 does not exist. And if the limit doesn't exist, then the function can't be continuous. But this graph, I'm going to put a mark at 3. So again, they said sketch any function. So to the right, the intended height of the function needs to be 1. So coming at 1 from the right, and then from the left, the intended height is 0. So maybe it's something like this. It can really be anything. That might be different from what I posted on my key there, but you get the idea. You have a split right there. It's not correct just to say, no, there's a jump in the graph. You've got to use your limit notation or say that the limit doesn't exist. Determine whether f of x approaches infinity or negative infinity as x approaches -2 from the left and from the right. So here's -2. From the left, the graph is going up to infinity, and from the right, so I'm going to say the limit as x approaches 2 from, -2 from the left of f of x is equal to infinity. And that's also equal to the limit as x approaches -2 from the right of f of x. So both of those are equal to infinity. Remember that this limit still does not exist. We're just being more specific in describing how or why it does not exist. All right, here's a graph of secant of pi x over 4. And we're still looking as we approach -2. So to the left, the graph is headed down to negative infinity, and to the right, we're headed up. So I'll write out both of these limits. The limit as x approaches -2 from the left of f of x is equal to negative infinity. And the limit as x approaches -2 from the right of f of x is equal to positive infinity. And again, both of those limits do not exist. We're just describing in which direction they're unbounded. All right, now for this function, they want us to fill in the table, determine whether f of x approaches positive or negative infinity as x approaches negative 3 from the left and the right by completing the table. So I didn't want to rewrite these numbers, but just to remind you how you can do this quickly, split here. So remember, you can go into y equals and type in your function. If you do alpha y equals, you get this little fraction, so you don't have to worry about as many parentheses. And then this is x over x squared minus 9. And remember, the purpose of putting this in y1 is not really to graph it. I don't really want to graph it, but I want to say alpha trace to call up y1. And I can evaluate at all of these different values. And then it's easy to just go up and grab that and change it to whatever the table says. So that's where I came about those. So once you filled in the table, you can see that these values are approaching negative infinity. And these values are, as you were going this way, are approaching infinity. Because remember, we're getting close to negative 2 on either side. And it's important to know which side is which. So, we're talking about at negative 3, these values are coming from the left. And these values are coming from the right. So the limit as x approaches negative 3 from the left of f of x is equal to negative infinity. And the limit as x approaches negative 3 from the right of f of x, that's the bottom row, that's equal to positive infinity. And again, both of those limits do not exist. We're just saying more specifically which direction they are unbounded. Find vertical asymptotes, if any. So this should be pretty easy. We're just setting the denominator equal to 0. So here it's x equals 0. I erased this number. Let me see what this was supposed to be. I always do this key and then, there we go. It's supposed to be minus 2. I do the key and then erase it, my work, so I can do this. Okay, so factor. The numerator does not factor into x minus 2x plus 1, so there are no holes in this graph. So there are 2 vertical asymptotes at 2 and at negative 1. For the next one, again, nothing cancels for number 20. So there's a vertical asymptote at 0, and there's one at 1. Okay, now trig we have to remember a little bit. So remember, secant is undefined when cosine is equal to 0. And the angles that make that happen are like pi over 2, 3 pi over 2, 5 pi over 2, etc. So we talked about this in our notes. The general expression would be pi over 2 plus pi k kes. K is an integer. You can add any integer, add or subtract any number, whole number of pi's, and you'll get to another asymptote. So here, though, we have this expression here. So I used u intentionally instead of just x. So we're going to set pi x equal to pi over 2 plus pi k, where k is an integer. Now we need to solve this for x by dividing by pi. And every term gets divided by pi, including the k. So x is equal to pi over 2 divided by pi is just 1/2. Pi over k divided by pi is just plus k. It's still true that k has to be an integer. So the asymptotes are happening at 1/2 radian, 1.5 radians, 2.5, 2.5 radians, etc. All right, for 33, determine whether the graph of the function has a vertical asymptote or a removable discontinuity at x equals negative 1. Graph using a graphing utility. I'm probably not going to take the time to do that, but you're welcome to. Removable discontinuity, when these are rationals, are just holes. Okay, so remember, we can factor to determine this. If a factor simplifies out of the denominator, it was a hole in the graph. So f of x is really just x minus 1, but still that x can't equal negative 1. So this is a line with a hole in it. That means that the discontinuity, there's a removable discontinuity at x equals -1. And when we say removable, we just mean we could construct a piecewise function that fills in the hole and makes it continuous. All right, my next one, we are finding, this is not removable. This is just find the limit now. Find the limit as x approaches 2 on the right of x over x minus 2. So we know the graph is unbounded. There's a vertical asymptote at 2. The question is, does the graph go to infinity or negative infinity? And remember, you can check this numerically. If I pick a number that's just a little bit to the right of 2, like 2.0001, and I plug it in for x, I'm just thinking about numerically, what would I get when I do this math? So if I subtract 2.0001 minus 2, I would be left with positive 0.0001. And so 2-ish divided by, this is like 1/10,000th, is going to be a large number, so you're headed to infinity. A number divided by a tiny number grows to infinity. So this limit does not exist. It approaches infinity. For the next one, kind of the same idea. So I know that there is a vertical asymptote at 1 because I would get 3 over 0 if I plugged this in. But if I think about plugging in like 1.001 to the top and the bottom, I'd get 3.001. That's not really the important part up there. This subtraction is going to leave me with negative 0.001. So a positive divided by a tiny negative is going to divide out to negative infinity for that one. Again, you can verify by graphing, but if we don't always have if we're not allowed to use a graphing calculator, you want to be able to analyze things numerically. It's also quicker, less room for error if you're trying to sketch by hand. All right, this one, now we're approaching 0 from the left. So when I take the limit of the first term, I just get 1. And then I'm getting plus 1 over, again, come at 0 from the left. So that's like negative 0.001, something like that. And so this is saying 1 minus infinity, 1 plus negative infinity. And 1 minus infinity is the same as just negative infinity because the 1 is inconsequential when you're subtracting infinity. Use a graphing utility to graph the function and determine the one-sided limit. So I've graphed this function ahead of time. We were told to look at the limit as x approaches 1 from the right of f of x. So here's 1. So definitely headed toward infinity. If you're allowed to graph, makes things a lot easier. Okay. This last one is kind of sort of looks more difficult than it is. So this says, according to the theory of relativity, the mass of a particle depends on its velocity, v. So mass is the output, or the dependent variable. It depends on the input, which is just velocity. So all of the other variables that you see are actually constants. M sub 0 is the initial mass when the particle is at rest. C is the speed of light. So those are both constants. This is just a number. This is just a number. And so find the limit of the mass as v approaches c from the left. So we want the limit as v approaches c from the left of m, which is some number mass on top, over the square root of 1 minus v squared over c squared. Now, I'm not going to worry about plugging in like 0.0001, whatever. Just direct substitute c into this because you're going to be squaring it. It really doesn't matter if you're coming left or right from this. So if I use direct substitution, I get some number on top over the square root of 1 minus c squared over c squared. I just plugged c into v squared. So this is like 1 minus 1. So now that's some number over technically 0, but remember, this is really like 0 point something. And I know it's positive because this was a positive square root. So, excuse me, even though I used direct substitution, I didn't plug in exactly c into c squared, so this won't come out to exactly 0. It'll be a little bit higher than 0, which means we have a number divided by something tiny. So the limit as v approaches c from the left of the mass equation, I'm just going to say m because I don't want to rewrite the whole thing, is infinity. All right, that's it for assignment number 5. Make sure that you come into office hours if you need help with any of this stuff up to this point.